In this lesson, we're going to look at traversable graphs. In lots of practical problems, we often want to find a trail in a network's graph. Recall, a trail is a walk with no repeated edges. A traversable graph has such a trail. Not all graphs are traversable. This graph is traversable. We can go from A to C, back to A, over to B, and back to C. The degree of A is 3, the degree of B is 2, and the degree of C is 3. You might recall that if a graph has exactly 2 odd degree vertices, then there will be a traversable path that starts and finishes at those odd vertices. This second graph is not traversable. Notice that each vertice has a degree of 3. Degrees are how many edges join to the vertices. You might recall this is a familiar problem from early years of maths, where you had to trace an envelope shape without lifting your pen from the page. This is achieved by adding another edge. So here we have exactly 2 vertices with an odd number of degrees, 3 here, and A and B now have an even number of degrees. So we should be able to traverse this starting at one of the odd vertices and ending at the other without lifting the pen from the page. And there we have it. So to be a traversable graph, first it must be a connected graph. All the vertices must be of an even degree, or exactly 2 vertices are of odd degree and the rest are even. From this it follows that a traversable graph will have a trail, or a circuit, or a cycle that involves the use of every edge in the graph. A non-traversable graph has more than 2 vertices of odd degree. So looking at the example from your textbook, in this first graph, let's count up the degree of each vertice. 2, 2, 2, 2. That's the number of edges joining. It has all even vertices, and that means that we can traverse it covering every edge only once. You can start and end at any of the even vertices. There's one example. In the second one, this vertice has a degree 2, 2, 3, 3, 2. So exactly 2 vertices are of an odd degree. That means you can traverse the graph as long as you start at one of the odd vertices and end at the other. Here you can see an example of that. In this final graph, this vertice 2, 3, 3, 3, 3. Well, we have 4 odd degree vertices, so it's not transversable at all. There are special types of traversable graphs. Eulerian trails and circuits focus on edges. An Eulerian trail includes every edge in the graph. The graph must have exactly 2 odd degree vertices. The trail will start at one of these vertices and end at the other. An Eulerian circuit includes every edge in the graph. The graph must have all even degree vertices. The circuit will start and end at any of the single vertices. In this example from your text, we're trying to see whether or not these have Eulerian trails or circuits. In this first graph, all vertices are even, so this one will have a Eulerian circuit. So it will start and end at the same vertex. Notice that there are many possibilities here. In graph B, we can see this has 3 degrees, this one 3 degrees, 2, 2, and 2. So it has exactly 2 odd vertices and the rest are even. So as long as we start and end at start at one of the odd vertices and end at the other, we can find a Eulerian circuit, a trail I should say. There we go. In this last example, we have a vertex of 3, 3, 3, 3, and 2. So there are 4 odd vertices, so there are no Eulerian trails or circuits, and of course that graph is not traversable. There are lots of situations where these can be applied. A postman wants to deliver mail without travelling along any street more than once. A visitor to a tourist park wants to minimise the distance they walk to see all of the attractions by not having to retrace their steps at any stage. A road inspector wants to inspect the roads linking several country towns without having to travel along each road more than once. Another special type of traversable graphs are Hamilton paths and cycles. These focus on the vertices. A Hamilton path passes through every vertex. It may or may not involve all the edges in the graph. So here's an example of a Hamilton path. Notice it's missed two of the edges, but it's got all of the vertices covered once. A Hamilton cycle is a Hamilton path that starts and finishes at the same vertex. So here it starts and ends at A. You follow this around. Notice it covers vertex D twice, that's fine, and ends at A. Unfortunately, for Hamilton cycles and paths, there's no simple rule to figure out whether a graph has one or not. It's a matter of trial and error. These types of traversable paths and cycles can be applied to many situations. For example, you plan a trip from Melbourne to Mildura with visits to Bendigo, Halls Gap, Horsham, Staywell, Oyen on the way, but you don't want to visit any town more than once. Hamilton cycles might relate to situations like this. A courier leaves her depot to make a succession of deliveries to a variety of locations before returning to her depot. She does not like to go past each location more than once. Or a tourist plans to visit all the historic sites in a city without visiting each more than once. Or you are planning a trip from Melbourne to visit Shepparton, Wodonga, Bendigo, Swan Hill, Natimbuk, Warrnambool and Geelong before returning to Melbourne, and you don't want to visit any town more than once. In all these examples, there'd be several suitable routes. However, other factors such as time taken or distance travelled may need to be taken into account in order to determine the best route. And this brings us to the next lesson of our work, weighted graphs and networks.